A high-pitched, monotonous beep echoed through the static of radio receivers across the globe in the autumn of 1957. It was a simple sound, yet it carried the weight of an unprecedented geopolitical earthquake. The Soviet Union had successfully launched Sputnik into low Earth orbit, inaugurating the space age and igniting a profound sense of vulnerability within the United States. That metallic sphere, no larger than a beach ball, was meant to demonstrate technological supremacy. No one could have predicted that tracking its faint radio transmissions would accidentally lay the foundation for a technology that now dictates the rhythm of modern human civilization. The immediate reaction to this celestial trespasser was a mixture of scientific wonder and Cold War panic. American defense agencies scrambled to understand the implications of a foreign object endlessly circling the globe, crossing sovereign airspace every 90 minutes. The sky, once a vast and empty frontier, had suddenly become a theater of strategic observation. The immediate imperative was not to build a rival system, but simply to listen, to track, and to understand the trajectory of this unprecedented artificial moon. Inside the quiet laboratories of the Johns Hopkins Applied Physics Laboratory, or APL, two young physicists, William Guire and George Weifenbach, decided to tune in. Armed with a microwave receiver and a profound sense of curiosity, they began recording the 20 megahertz signal emanating from the Soviet satellite. They were not acting on military orders. They were simply scientists captivated by the novelty of a human-made object broadcasting from the vacuum of space. Their makeshift listening station, hastily assembled in a Maryland office, captured the exact frequencies falling from the sky. As they analyzed the recorded audio tape, they noticed a distinct, predictable anomaly in the transmission. The pitch of the beep was not constant. As Sputnik approached their position, the frequency of the radio waves compressed, raising the pitch, and as it flew away, the waves stretched, lowering the pitch. This is the Doppler shift, the exact same acoustic phenomenon that causes a passing ambulance siren to change its tone. By meticulously measuring this shift in the radio frequency, the two researchers realized they were capturing the precise velocity of the satellite relative to their listening station. The data plotted on their charts formed an elegant mathematical curve. Guire and Weifenbach quickly realized that this curve was not just a curiosity, it was a geometrical key. By running the Doppler shift data through a recently acquired UNIVAC mechanical computer, they discovered they could calculate the exact orbital path of Sputnik with astonishing accuracy. From a single stationary point on the surface of the Earth, they had successfully mapped the trajectory of an object hurtling through space at 18,000 miles per hour. The sheer elegance of this deduction was staggering. By merely listening to the distortion of a simple radio wave, humanity could trace the invisible highways of orbit. The mathematical relationship between the observer and the observed was absolute. This breakthrough demonstrated that the physical laws governing the universe could be leveraged to bridge the vast silent void between the Earth and the heavens. The implications of this acoustic geometry would soon capture the attention of minds far beyond the civilian laboratory. The theoretical challenge still loomed, but it was about to be inverted. Frank McClure, the deputy director of the Johns Hopkins APL, reviewed the researchers' findings and recognized a profound strategic opportunity. If a known location on Earth could be used to determine the unknown orbit of a satellite, the mathematical reverse must also be true. If the exact orbit of a satellite was known, listening to its Doppler shift could reveal the precise unknown location of a receiver on Earth. This inverted concept arrived at a critical juncture in the Cold War. The United States Navy was actively developing the Polaris program, a fleet of nuclear-armed submarines designed to serve as a hidden underwater deterrent. However, for a ballistic missile to accurately strike a target thousands of miles away, the submarine had to know its exact starting coordinates in the middle of a featureless ocean. Traditional celestial navigation was useless if the sky was overcast, and surfacing to take a reading was highly dangerous. The Navy desperately needed an artificial, all-weather star. McClure's insight provided the blueprint. The military commissioned the development of the transit system, an ambitious project to place a constellation of navigation satellites into orbit. The leap from passively listening to a Soviet sphere to actively engineering a reliable global positioning network required unprecedented advancements in orbital mechanics, radio transmission, and data processing. The accidental discovery during the Sputnik crisis was now the driving force behind a massive defense initiative. The early attempts were fraught with the harsh realities of early spaceflight. After a failed launch in 1959, the Transit 1B satellite successfully reached orbit in April 1960. It was a primitive machine by modern standards, broadcasting continuous signals for Earth-bound receivers to analyze. Naval vessels equipped with massive, room-sized computers could now listen to the satellite pass overhead, measure the Doppler shift, and calculate their position on the open ocean to within a few hundred meters. The system was a triumph of engineering, yet it harbored severe limitations. Transit provided only two-dimensional positioning, yielding latitude and longitude, but no altitude data. Furthermore, because there were only a few satellites in low Earth orbit, submarines often had to wait hours for one to pass overhead. It was a periodic fix, not a continuous stream of navigational awareness. The echoes of that foundational idea followed, demanding a more robust and immediate solution for the rapidly accelerating pace of modern warfare. The military apparatus required a system that could provide instantaneous three-dimensional coordinates anywhere on the globe, 24 hours a day. The Doppler method, while brilliant, was too slow and mathematically constrained for the dynamic needs of supersonic aircraft and rapidly moving infantry. A new theoretical framework was required, one that shifted the foundational mechanism from measuring frequency distortion to measuring the absolute passage of time. The new concept relied on the fundamental equation of distance equaling rate multiplied by time. If a satellite broadcast a radio signal and the receiver knew precisely when that signal was sent and when it arrived, it could calculate the distance between them, given that radio waves travel at the speed of light. By locking onto signals from 4 different satellites simultaneously, a receiver could triangulate its exact latitude, longitude, and altitude. But this required clocks of unimaginable precision. To measure the speed of light over orbital distances, an error of a single millisecond would result in a positioning error of nearly 300 kilometers. Mechanical or quartz clocks were entirely insufficient. The solution lay in atomic clocks, devices that measure the hyper-stable, microscopic vibrations of atoms, typically cesium or rubidium, as they transition between energy states. These clocks do not tick through gears. They count the fundamental, unvarying rhythms of quantum mechanics. Placing these highly delicate quantum instruments into the violent, radiation-soaked environment of space was considered nearly impossible. Yet, under the direction of Roger Easton at the Naval Research Laboratory, the Tomation Project successfully launched experimental satellites carrying quartz and eventually atomic clocks. Easton proved that highly synchronized timekeeping from orbit could provide the continuous, three-dimensional navigation the military desperately sought. The ability to broadcast perfect time from the heavens became the new architectural pillar of global positioning. By the early 1970s, a bureaucratic battle was raging within the Department of Defense. The Navy championed its Tomation project. The Air Force was developing a rival system called Project 621B, which utilized a different signal structure, and the original transit system was still in heavy use. The fragmented efforts threatened to derail the dream of a unified, comprehensive navigation network. The technological pieces were scattered across different branches of the military, awaiting a visionary to force them together. Over a tense Labor Day weekend in 1973, Air Force Colonel Bradford Parkinson gathered the key architects of these competing programs in the Pentagon. Parkinson ruthlessly synthesized the best elements of each project. He took the orbital configuration and signal structure from the Air Force, the atomic clocks from the Navy's Tamachian, and the foundational orbital prediction models born from the original transit system. This forced marriage birthed the NAVSTAR Global Positioning System. NAVSTAR GPS was designed as a constellation of 24 satellites arranged in 6 orbital planes, ensuring that at least 4 satellites would always be visible from any point on Earth. Each satellite was essentially a flying atomic clock, continuously broadcasting its position
and the exact time. The receiver on the ground would do the heavy lifting, comparing the arrival times of the signals to calculate its own exact location. It was a masterpiece of systems engineering.
Yet, as the first NAVSTAR satellites were being built, a profound theoretical hurdle emerged from the realm of pure physics. Albert Einstein's theories of special and general relativity dictated that time is not absolute. Because the satellites were moving at immense speeds relative to the Earth, special relativity stated their clocks would tick slower. Conversely, because they were 20,000 kilometers away from the bulk of Earth's gravity, general relativity stated their clocks would tick faster. The net result of these relativistic effects was that the atomic clocks in orbit would run 38 microseconds faster per day than clocks on the ground. 38 microseconds sounds negligible, but at the speed of light, it translates to a navigational error of over 11 kilometers per day. The engineers had to program the satellites to artificially slow down their atomic ticking before launch. The system would literally fail if it did not account for the warping of space-time. As the constellation slowly populated the sky throughout the 1980s, its military utility was absolute, guiding munitions and troops with terrifying precision. The system was highly classified, with civilian access heavily degraded or entirely blocked. The initial concept of a military-only utility was firmly entrenched. It took a devastating international tragedy to force the technology out of the shadows and into the public domain. In September 1983, Korean Airlines Flight 007 inadvertently strayed into restricted Soviet airspace due to a navigational error and was shot down, leading to the loss of all 269 people on board. In the aftermath of this disaster, President Ronald Reagan issued a directive to make the GPS signal freely available to civilian aircraft once the system was fully operational. The goal was to ensure such a catastrophic navigational failure could never happen again. The true explosion of this technology required one final massive leap in engineering: miniaturization. The first GPS receivers were massive, power-hungry boxes that required a jeep to transport. Through the relentless march of Moore's law, engineers shrank the complex radio receivers and processing algorithms down to a single silicon microchip. The massive naval computers of the transit era were condensed into a component small enough to fit inside a mobile phone, consuming mere milliwatts of power. Today, the system is an invisible utility, as fundamental to modern infrastructure as electricity. While we associate it with driving directions, its most
Critical function is timing. The synchronized atomic time broadcast by the constellation regulates the global financial markets, timestamps every cell phone call, and synchronizes the alternating current of international power grids. If the satellites were to suddenly go dark, the modern world would not just lose its way. Its digital heartbeat would stop entirely. We exist in a state of profound dependence on a faint radio signal, weaker than the background radiation of the cosmos by the time it reaches our devices. The sheer ubiquity of satellite navigation masks the staggering complexity of its operation. Every time a blue dot appears on a screen, your device is silently consulting a fleet of atomic clocks, hurtling through warped space-time, performing relativistic mathematics in fractions of a second. The journey from the panicked observation of a Soviet satellite to the invisible backbone of global infrastructure reveals the deeply unpredictable nature of innovation. The profound realization that sparked this revolution was not born from a desire to navigate city streets, but from the simple human curiosity of two scientists tuning into a beep in the dark. The unexpected origin of GPS from Cold War Sputnik signals stands as a testament to how the act of merely listening can inadvertently map the future of the world.